Hello and welcome back to ST118 Statistics and Applications Session 5. In this session, we'll examine the two population median test. And we use a plural here because just like the parametric test situation, there are two tests involved. There are branches because we want to, the goal is to find or test eta, the population median, right? So there are two branches depending on where we are heading, right? So it is the pet test and the unpaired test. Now this separation is really more due to the inherent nature of our test, the experimenter's goal, the desire, right? So because we were saying in the parametric video that for pet test, it's able to have some noise cancellation effect, right? That the other measurements, other factors, other influences that may affect our intended measurement. Our intended measurement can be the GPA of siblings from the same family, right? We were saying that. Then when we pair them, when we pair up the siblings from the same family to compare their GPA, then we can answer our intended goal of whether young siblings tend to perform better than older siblings, because of generational effects and whatnot. So in those cases, pairing allows us to be able to defend our outcome better in case other people bring up this noise effect. Other factors could have led to this conclusion, right? What makes you think that this outcome, whether reject or not reject H naught, is entirely due to the younger sibling effect, right? Okay, so that pairing and unpairing really still persists here, right? So we still need to have non-parametric test methods that will allow us to carry out these in a way that is statistically fair, right? And reliable. Okay, so under the PET test, we will use the Wilcoxon signed rank test. If it sounds familiar, then yes, congratulations, you have done your homework well. You did watch and remember well the previous video to this, which was about one population median test. And in that test, we were using Wilcoxon sign rank test. It is exactly the same with a bit of pre-processing, that's all. And it is no surprise because it is the mirror image of one population mean test, t-test. One population t-test, right, can be carried out using two population paired t-test by setting the other population, the one that is being subtracted by, into zero. So we are like saying for one population test, it is as if it is two population paired tests with the paired 2 population being set to zero. So mathematically, then it will be entirely the same. So it is no surprise that we are using the Wilcoxon sign rank test again for paired test. Except this time around, we don't set it to zero. We really have sampled values for the second population. And by introduction, we will use the Mann-Whitney U test because the test statistic frequently is represented by U, right? And Wilcoxon W, but we don't call it W test. Mann-Whitney, the U test, right? So these two tests will be sufficient, and non-parametric tests like Wilcoxon and Mann-Whitney, they deal with small sample sizes well, and for larger and larger sample sizes, software modules will internally numerically approximate it using other quicker calculations, maybe normal approximation or whatnot, to do pretty reliable and fast and respectably high precision calculations of the test statistics and p-values and whatever is necessary. Then we can leave it to the software developers to do that. Okay, let's just go straight into our example to look at how we can carry out these tests. So example illustration. Okay, say for example, we want to test whether, right, median of differences before and after training is 0. In other words, the training has no effect on the employees, right? The maybe in terms of productivity, memory boost, camaraderie, relationships, and whatnot. Okay, so you can see that it has got wide applications, the before, after, to see whether the stimulus, right, in this case, the training, is effective. Of course, it can also be some sort of a ginseng soup, chicken essence, drink, coffee, newly branded high caffeine coffee, whatnot, right? To test whether it is effective in, or the effect is really there, significantly detectable by measurements and so on. So it can be generously applied to many situations when we need to compare. Remember, the goal of two population means tests, and in this case, medians tests, they are to compare two items, two entities, two products, two models, two whatever, right? So in this case, it's before the employees will behave or measure this way, their productivity. After the training, the employees' measurement. So the physical person group is the same, but the timing is different, right? So this is again also very frequent area of applications for comparing two population medians. Okay, so here we write down, okay, so we write down H naught is eta equals to 0. And H1 is eta not equal this way, that way, this way, not equal to 0. Okay, so meaning in this case, training is not useful. Okay, useful or not is a very, subjective, wishy-washy term, right? So we are going to convert to, test scores or something. So the measurements, right? So the median of differences of measurement of test scores or performance scores or examination scores for the employees, okay, before and after. So the measurement is not mentioned here, but you can plug in any suitable measurements that is going to be efficiently obtainable and reliable, right? So here then the conclusion is training is useful, right? Because the median difference is no longer 0. Well, we can say the D, remember the delta population, huh? So the median of the difference population. So where eta of D, right, is population median of the delta population and delta population, right, is the population of di equals to x1i or xi1 minus xi2. This is before, this is after. So the 1 and 2 convention, we used it in the parametric test example, right? So we try to follow it. But here the 1 is referring to what is it? Before, and 2 is after. Or of course we can define it as 1 is after, 2 is before. So up to our definition. Now here we use not equal to 0 equal to 0 because this is most frequently used. But of course, if it is not equal to 0, it could mean that after the training, the performance is worse, right? That's why it's different from 0. So, but oftentimes, if it is significant, that means we reject H naught, right? Then whether it's better or worse, we normally can tell, right? In fact, even if you don't measure, somehow management is already able to detect. It's very distracting, actually. The employees start playing games and forgot about work, right? So productivity goes down, and after training is even worse. Okay, so anyway, let's come back to this. Okay, so what we do is that we start to sample, make measurements, right? And we will obtain samples. And because they are paired, it's a good idea to have some sort of a serial number. And we say something like before and after. Right, so first pair, first employee, because we measure, right? 10.2, 8.1. Second employee, 9.5, 7.9. Third employee, 8.7. Don't worry, this won't go on forever. Just give me time for 5 pairs, right? Because actually 5 is still just borderline case where the critical value tables start to show non-zero numbers. Let me start to show something interesting, but never mind, we'll live with that because we don't want to really spend the whole video just writing down numbers. Okay, that's all. Okay, so we sampled from 5 employees. Not if we step back, we should understand that we are touching reality 5 times only, right? So maybe it's a big MNC of 50,000 employees. So this is hardly enough. Don't expect 5 employees feedback or performance before after to represent 50,000 people, right now, yeah? So so right at the start, the hard work is not enough. But when we feed this into the meat grinder, the Wilcoxon sign rank test, will that choke or not? Answer is no, it won't. Will it be? It's a bit like when you have small sample size, the meat chunks that are fed into the meat grinder, which is the hypothesis test algorithm. For parametric tests, the t-test and all that, they start to choke, right? They are like, cannot grind well enough. They start to rattle, doesn't perform very well. So it's only when you have more samples that maybe the input is already grounded to very fine cubes, right? Small little meat chunks, then the grinder becomes very smooth. But here, no problem. You just feed them in, the grinder will still grind very well. Okay, so what we want to do is to first step compute the DI, right? So the DIs we subtract and we obtain, so these are our calculations. So we obtained 2.1, 1.6. Please check my calculation. If there are mistakes, then please live with it. So long as you know what I'm trying to do here, right? So sometimes I may not copy down or write down the calculation correctly. Okay, so if you remember, this was our starting point, right? Do that and remove any zeros. So need to remove any zeros. Need to remove any zeros, but we don't have any. If we do remove any zeros, then the shrunk count is our n, is our so-called sample size. So for now, our sample size is okay, since no zero, n equals to 5. So if there is 1 0, n equals to 4, as in the previous one population median test example. Okay, so from here, then what do? We start to rank the absolute values. We start to rank the absolute values. That means we ignore the sign and just look at the magnitude and sort them. So rank them is a mathematical way of saying computationally sort them. So we rank, and of course you will get, this is number 1, right? And 0.5 is number 2, and 0.9 is number 3, because we ignore the minus sign. Yeah. So in this case, we do the ranking. Where's our rank? I don't have a place to write the rank. So let's write the rank. Absolute value of rank. Well, rank based on absolute value, but I just use this notation. So this will be number 1. This will be number 2. Number 3, I hope you agree, right? And then number 4, and then number 5. Yeah. Now with 5 values, it's quite easy. We just eyeball it. In the larger data set case, we say sort them, but of course computationally there are more efficient ways to deal with it very quickly, because you don't really want to move the numbers and align them from small to big. You actually just want the ranking. Okay. Then the next steps are just exactly the same as what Wilcoxon sign rank test for one population will do, and which is to extract the ranks, right, and calculate W plus. So our W plus is the sum of all the positive ranks, which will give us 5 plus 4 plus 5 plus 4 plus 1 plus 2, so that's 12. And our W minus is the sum of all the negative ranks. So this is easy. We only have one negative value based on the data. Negative ranks means the rank that is associated with negative value. So otherwise it will be very wordy. So pardon me for writing this short and maybe not very correct phrasing, negative ranks. Okay, so there's no negative ranks. We still add the positive value here, but it's the rank associated with the negative input data. So we put down 3, and that's it. So we now have 2 numbers, W plus, W minus, and our test statistic is the mean of W minus and W plus. So we get 3. Okay. And we need to do table lookup for the Wilcoxon distribution, right? And the distribution will give us WC. Where's our WC? So our WC is going to be something like 0. So in other words, the test statistic 3 has to be less than 0, less than or equal to 0, in order to reject H0 at alpha equals to 5%. So alpha 5%. Right? We should have a distribution. Well, because for generally slightly larger than 3, 4, and 5, we will have some sort of a distribution shape for Wilcoxon, right? That looks something like this. Except this number could be large, because some large as in bigger than 3, but smaller than 27. So some numbers. So I will just put something like maybe 20. Okay. So it is not really smooth. It is made up of a lot of vertical bars. Oops. Okay, and because the test statistics will be values here. And so it is here that we will get our, it is the 0 here, right, that will give us the critical value, TC. Okay, why? Because the distribution is discrete, right? So we will have a bar, and the bar has height. Height is the probability, and the height itself is larger than 5% already. So we will not be able to go beyond the 0. So no choice, right? So in other words, almost any test statistic we get will be larger than 0, right? Very very likely to be larger than 0. So we will not be able to reject. So if we put a Google pin, our Google pin will be here, and this will be number 3, right? And our p-value will be larger than 0.05. So we will conclude based on this and say that since, right? So since W equals to 3 is not smaller than or equal to WC, which is equal to 0. Or you can say since p-value is, I use Python and software to compute this part, the p-value. All right, I got 0.3125, and clearly it is bigger than 0.05, so we should reject. Same conclusion here, right? We reject, sorry, we do not, because only when it's smaller. We do not reject H naught and conclude whatever H naught says, right, in English. And since the English translation is already there, we can then just say that training is not useful. Training is not useful at 5% significance level. Okay, so in other words, when sample size is small, almost always we'll just stick with H naught. There is no reason at all to reject H naught. So that would be the tendency for non-parametric methods if you use small sample size, right? So it doesn't contradict the fact that when we say non-parametric methods, they are robust, they can take in small sample size, they don't rattle, they don't choke, right? They still give very solid, reliable conclusion. But it's like a pixelated picture is still a picture, right? It's still trying to show you the reality picture image. But if you didn't use good camera with high resolution, you just cannot show the details. Just impossible, right? So that's the whole idea here. So in order to show kind of like stronger evidence, right? We might wonder, 5, can you do really represent 50,000 employees or not, right? So then you might have to spend more time, more budget, more patience and manpower to gather from maybe 5,000 employees in order to make your case even stronger. Okay, so that's for the test. Next, we want to talk about the unpaired test. So let me do a bit of demarcation, carve out the real estate. Okay. All right. So next, we want to use the same example, right? And this time round, we want to use the unpacked test. So because we were using the same employee, right? So it will have noise cancellation effect if the employee is let's just say the training is, let's say, going to jungle survival training where you have to help buddy and all that stuff to build up camaraderie, right? So if the result is do not reject, right? So again, it can be cast in doubt, and we say no because it's based on the same employee, right? Because people can say you are using the employee who is fit, and you compare with another employee who is not fit, before after, not really fair, not really good. No, I'm using the same employee, right? So if the employee is very fit, then before and after there should still be an improvement. And for the employees who are less fit, before and after there should be even more visible improvement in the productivity, right? But yet, right, given the same employee, I still don't detect any difference. Okay. Next, we will use back the same example. So I don't want to rewrite this again. So we're going to test whether the median of differences. But of course, the phrasing needs to be a bit more fitting, right, for the unpaired test situation, because we will not be able to say the median of differences because there is no calculation of the delta population, right? We're not going to create a tentative delta population of differences, so it cannot be phrased as this. So we want to say something like want to test whether the differences of medians, right? Of basically population medians are population medians. Now let me move myself so that you can see what I've written. Okay, so we want to test whether the difference of population medians, this time round, it can still be before and after training, except this kind of design may designing the experiment this way using different people before and after the training may not be very suitable, right? Because it may not make much of a sense. But we can certainly say difference of population medians medians of productivity or something else. Example of productivity medians, productivity medians, right? Okay, between day shift employees and night shift employees are the same. Okay. Is 0. Okay. So we have this management concern. We want to see if there's no training now. There's just question mark, right? Maybe there was some complaint. Maybe there was some incidents. Maybe there's an annual report showing some visible differences, right? Whatever it is, somebody suggested there's a difference in the productivity of day and night shift. So if there is really a difference, what's the problem? Is the problem due to poor pay, right? Not enough overtime pay, not enough night shift compensation. If so, maybe you should give them a bit of motivation, something like that. So we would translate this into H naught of eta daytime minus eta nighttime, right? Okay, so this is equal to 0. We talked about this in the paired test example, in the unpaired test parametric test examples, right? So eta 1 minus eta 2 is not 0. Right, so here we can then say that it is day and night shift, same productivity, right? Day and night shifts have same productivity. Okay. And here we would say day and night shifts. Now, let's try to cast suspicion have different productivity. Let's try to apply the same suspicions to our unpaired test as the paired test. So we say, hey, your result to reject H naught or not to reject H naught, right, is not reliable because one works in the day and the other one works in the night, and you're using two different groups of people. Those day shift workers are not the same as the night shift workers, right? Well, this kind of setting, I think hardly can there be anyone trying to do paired tests. You're like saying the same person has to work day shift and then has to work night shift, right? Whether you say it's alternate days or alternate weeks or what, it's just not very practically possible. Okay, just imagine who are these workers? They are working for money, right? They have to survive, isn't it? They have to feed themselves, feed their family, feed their parents, feed their children, maybe. So if I make arrangements to do night shift, then my routine, right? My being at home routine or whatever routine with family, with my interaction with all the family and extended family will be settled down in some sense, even if I work night shift, right? So long as it's stable. But to have night shift, then day shift, night shift, then day shift, then you're just upsetting people's lives. So normally it is not very common, right, to see a lot of workers who randomly switch between day shift and night shift. Very seldom. If there's a switch, it's also perhaps after half a year, after 1 year, maybe because children, instead of attending morning school, now it's afternoon school, so I don't mind this and that, something like that. So it won't be alternate days, alternate weeks. But then, of course, your experiment is carried out in maybe 1 week or 1 month or several days. So you're not going to ask people to do that, right? So of course you will have different workers for day shift, different workers for night shift. But that's fine, right? And then you may have more workers in the day shift than night shift. And in that case, your sample size likely cannot be the same. And if your sample size cannot be the same, then you cannot do paired test, whether it's parametric or non-parametric. So that's why unpaired test in this case still stands because of circumstances, because of this environment, right? You can still defend the design, right? Our experimental design that it is a unpaired test. Now, because our sample size is small and we like our conclusion to be defensible, so we are going to use the non-parametric test. For unpaired test for two population, it's called a Mann-Whitney U-test. And the way it goes is like this. So we capture samples, right? X1. Let's just say it is 1.2, 3.1, 5.4, 7.8, 9.0. It happens to be in ascending order, but doesn't really matter. So this is sample size is 5. Then second set of sample from the night shift. Indeed, right, we have fewer samples here. 2.3, 6.2, 10.5. Let's say these are productivity readings. So N2 equals to 3. Okay, so far so good. And Mann-Whitney, because it's non-parametric, just like Wilcoxon, we already had a taste of that, will end up trying to rank values. We'll end up trying to rank values after all. And we will, the way we rank will be to combine them. All right, just like merge them and sort these values. Okay, so we combine them and sort them by values. So we will put down 1.2, 3.1, 5.4, 7.8, 9.0, 2.3, 6.2, 10.5, right? So these are the data values. We tentatively combine them, right? Then we rank them. So the data, merged data. Then the rank. So we rank them. Basically, just look at the data and rank them. So clearly this is 1. So rank number 1, right? And then we have this number 2. Okay. Just to make sure we can read the line very clearly. What else? We have this 3.1 is rank number 3. Okay, 5.4 is number 4. And 6.2 here is number 5. 7.8 here is number 6. Right, this value 9 is number 7. 10.5 is number 8. Okay, and it is clear to see that this part, right? We wrote down 1.233 until here, right? This part, these are all data from population 1 or population sample population. Okay, and these are data from sample 2. Okay. Then what do? We will produce 2 rankings, a bit like the W plus, W minus that we saw earlier on. We will then combine them. All right, so what's our calculation like? Okay, so we can look at our UV, let's call it V, right? So the V is not U yet, right? So V is the sum of ranks. For sample. All right, so we have V1 equals to 1 plus 3 plus 4 plus 6 plus 7. Okay, try it out and you get 21. Then we have V2 equals to 2 plus 5 plus 8. That's 15. Yes. Okay, so we have V1 and V2 and they are to be fed into U1 and U2. Okay, so now we finally see the U test statistic, but we still have 2 sub-U's. So the U1 is V1 minus N1 bracket N1 plus 1 over 2. Okay, and this is the formula for Mann-Whitney's test statistic. So we get 21 minus N1 is, where is it? 5. So 5 times 5 plus 1 over 2. So if you calculate this, you should get 6. Then we have U2 is the same, but using values from sample 2. And we get 15 minus N2 is 3. So 3 plus 1 over 2, and we get 9. And finally, the U test statistic is going to be, no surprise, something like the Wilcoxon test statistic, to use the minimum of U1 and U2. So answer is going to be 6. Okay, and of course the Mann-Whitney test, for Mann-Whitney test, we will have to use the Mann-Whitney critical table. Okay, so we will check using the critical table. So from table, right, we get the critical value UC equals to 1. So again, just like Wilcoxon, we need to have a test statistic being less than or equal to UC in order to reject H naught. So since U equals to 6 is not less than or equal to UC, the critical value, we fail to reject, right? We do not reject H naught and conclude that since we do not reject H naught, we look at H naught and say what it says in English, right? And preferably not mathematically, because the whole point is to solve problems. So don't keep it very cryptic. So just say day and night shifts have same productivity. So we conclude that day and night shifts have same productivity, same median productivity, right, at 5% significance level. Okay, all right, so that's the sort of a big idea involving Mann-Whitney test. Now, what happens if we have a one-tail test? Well, for one-tail test, then we need to look at the half of the look at the two-tail test with double the significance value. So typically, if tables are given for two-tail tests for 5%, right? Then for one-tail test for 5%, you want to look at the two-tail test table under 10% significance level, right? So that one-sided is going to be 5%. So that's similar to the use of exact table. And also, this will be less than or this will be greater than, right? And we will then need to consider using either U1 or U2 alone. So no more minimum, right? No more minimum. You either choose to use U1 or U2 depending on whether it's less than, greater than in that sense. So minor adjustments here and there, and we can do it. But the easiest is still to consider the equal to 0 case. All right. So far, that's what I want to do with the example. And of course, it's always educational and helpful to try to look at or peep into what the distribution, the shape, what the distribution for Mann-Whitney looks like. The Wilcoxon distributions or family of distributions, we have examined that in the one population median test already. So if you like to see the distribution shape for Wilcoxon, do click into the one population median test to have a look. Right. For now, I'm just going to share with you again through some experimental coding that I tried to see the shape of Mann-Whitney distribution. Because if you search around the internet, it's a little bit rare to find the U-test statistic. Okay, so so I like to share with you guys this this drawing. Okay, so this is the U-test statistic, and for the case of what is it? H naught eta 1 minus eta 2 equal to 0. H1 eta 1 minus eta 2 is not 0, right? For this generic case. Then what happens? A bit not surprising if you have seen the Wilcoxon signed rank test distribution. For the case of, I did it for 3 different sample values, and I use n1 equals to n2 equals to 3, because actually it will be a 2x2 table of graphs, 2x2 table of two-dimensional graphs, right? So it'll be a lot to draw and to compute. I certainly can run them automatically uh, to generate the graphs, but what I'm interested in is just to share some feel of the shapes. And even when I assume symmetrical values, already some lessons come out, right? So let's see, 5, 6, 7. So 5, 6, 7, 1, 2, 3. Okay, so not surprisingly, the Mann-Whitney tables, they are somewhat symmetrical, and they are uh, stickish. In other words, doesn't mean they're sticky, but they're stickish in the sense that they are very much like bamboo stick, right? So like this, something like that. And I should be, yeah, like this, and then I should be drawing bars so that they are more visually presentable or nicer, but also a bit distorted or distorting, because it seems like the test statistic can be 0.5, 0.6, 0.7, and the critical value, that is, can be 0.5, 0.6, but actually, no. Okay, so when we have this, then what happens? Yeah, it's going to look something like this, right? So if you kind of put a cloth on top and drop it down, and the cloth starts to stick to whatever is supporting the cloth, then you will see this shape. Huh? So first thing first, it reviews that the points are on the integer values. Second thing is that it looks symmetrical. Now I use simulation, so it's a little bit, it's going to jiggle a little bit if I run it multiple times, right? But it does show some sort of a symmetry. And of course, if we run it a few more times with different or increasing sample size, we twist that a little bit more. So this time around, I have n1 equals to n2 equals to 10. So increase the sample size. Usually the shape changes a lot when 3 goes to 4 to 5 to 6. The initial increase in sample sizes make the distribution change a lot. I think that's not surprising. It's a bit like if we touch something new one time and say, guess what this is, right? You touched something furry and soft. Just one touch, you say, very hard to guess, right? It could be a doll, it could be actually a dog, right? It could be an actual dog, it could be a doll, it could be carpet, it could be blanket. Yeah, who knows, right? So you touch and say, I think it's a doll, right? It's a polar bear doll or whatnot. And if you can't decide, then you might say, give me another try, right? So you touch 2 times. Maybe one time nearer the so-called head, one time nearer the bottom to test the extreme. Is it a moving animal or so with the initial increase in sample size, you tend to have a great deal of improvement in your guess. Likewise here, right? So the change in the shape is quite drastic to show that improvement in knowledge of the reality. But when there's always a but, right? When the sample size starts to get larger, like increasing from 50 to 51, you are not going to expect big changes, right? The graph will change very slowly and subtly, and you only see big changes in shape when you double it, perhaps, right? The sample size. Okay, so we have again some sort of illustration of symmetry, but this one was a little bit more shocking to me. Not shocking, but a little bit more revealing. Guess what I'm drawing now? Yeah, it looks like a normal distribution now, right? So, and because of the way I obtained this graph, it is spiky, and that is not not wrong, right? So it is based on the integer positions. And just try to continue this, all right, simulation. I continue on and obtained another one. This is the last one. Okay, this time around, I increased the sample size to 30. 30 is a magic number that is considered large, right? Provably, central limit theorem quotes this number, 30. So we have 30 as something large. Beyond that, the graph changes very in very minor ways. But certainly one part of the graph you can already see, just like Wilcoxon, the number one, the range is always from 0 to something finite. So for 3, this becomes 9. That's it. 10 is not possible. And for 10, this becomes 100. And then for 30, this becomes 700. And of course, we also have 500, 600, something that is quite central, right? 3, 2, 1, 0. So, all right, some this should be 450, 350, 300, 400, 500. Sorry, this should be 350. Okay, so 350 is here, and I get something like this, tapering off to a bit close to 0 on the y-axis, but not 0. Okay, and it ends there, finite. That means it doesn't like keep having a longish tail, just like normal distribution, all the way stretching to positive and negative infinity. Okay. So rather interesting, right? We're almost like landing in Mars. Haven't seen this kind of graphs before, right? Okay, so using this, we can then try to look at our example here. Our example is going to be closer to this case, right? So it's got two different number, 5 and 3. So we can just imagine the graph looking like this. And the Google pin is going to be landing on 6. Right? 6. Very large number. Right? And the critical value is 1. In other words, the critical value is here. So this is our alpha. Our alpha, right? So our alpha, probably this is not up to 1 here, right? Is not yet alpha, maybe slightly less than alpha. Okay, slightly less than alpha. But if we put 2, then it will be exceeding 5%. So that's why the value is still 1. So that's the thing. And of course, our p-value, where's our p-value? Our p-value is going to be something like this area. On this graph, it shows up like much larger than 50%, right? But more because I'm using 3 and 3, not 5 and 3. So in the actual case, I use software to obtain the p-value, and the p-value here I get gave us something like 0.3, wait, let me see. 0. Is 0.7857. So not bad, an approximation. Okay, all right. Now, calculating the p-value exactly is going to require a different code from generating the distribution here, right? Because you want some exactness, right? Or starting from the test statistic. And in some cases, the test statistic can end up having a bit of a fraction with, adjustments in to account for duplicated ranks, zeros, and whatnot. So in that case, to get more precise p-values, you really have to tune the code a little bit. Not much of a difference, but then there's some tuning needed to get more precise p-values. But to see the distribution, it's easy. Just randomly throw darts to try to get the U-test statistic, right? That means to generate random numbers to crunch through and keep getting a lot of U values, and then that will be the darts that will be thrown on this diagram, and then gradually it will build up a histogram, gradually revealing the shape. So that's the advantage of using simulation techniques, something we can talk more about in the topic involving simulation. That's what I have to share with you today on the two population median tests using non-parametric methods. Thank you for your attention and see you in the next video.